Hi, everyone. I'm Michael Heiber, and today I'm going to be teaching you guys a little bit about ANT. So let's first start by asking, what is ANT? At first, I'm just going to kind of go over a high-level description. So really what it is it's an ultra-low power wireless protocol. It's a software protocol stack that runs on the 2.4 gigahertz radio devices. Data is transmitted between devices wirelessly, and it is designed for the personal network area applications. These devices are ultra low power, so they can run on coin cell batteries for over a year. And it also provides reliable communication. Next is it has no network masters, unlike other wireless protocols. So what this allows is for really complex networks, and we're going to talk a little bit more about this later. Next, it works really well in crowded environments. So ANT nodes avoid each other, allowing for coexistence of multiple ANT nodes within the same RF space. In addition, there's also frequency agility, which allows the ANT nodes to monitor the channel's performance and allows them to switch frequencies when the performance starts to degrade. And also, so as you can see here, you can have multiple ANT nodes running simultaneously, and your network will operate just fine without zero crosstalk. And ANT is ad hoc capable, and that gives you the ability to create and destroy connections on an as-needed basis. Network configurations are extendable and are not fixed, and the channels can be set up on an as-needed basis. So as you can see here, you can easily add in nodes to your network as needed. And finally, there's the ease of development. So the ANT protocol encapsulates the physical network and transport layers. This allows developers to focus on the application layer use case and not how the data is being sent over the air. And there's tools, sorry, the microphone's kind of cutting out here. There's tools available for embedded, PC, and Android applications. Where can you find these development resources? You can find them on our website at thisisant.com. It's a great place to find developer tools such as PC applications that allow you to simulate and create ANT nodes. There's lots of documents there, such as our ANT and message protocol doc, which is going to go into a lot of detail into what I'm talking about here today, as well as other useful documents such as interfacing with ANT modules. And there's also a great form and places to. So let's go a little bit deeper into how this works. So let's first talk about the ANT node here. ANT itself is not a radio. It's a protocol that operates on the 2.4 gigahertz space. So this ANT shows the layers of your ANT node. It is made up of an ANT embedded chip containing the 2.4 gigahertz radio transceiver and the ANT protocol stack. The ANT protocol stack provides efficient control of the radio through the ANT firmware layer and encapsulates the complexity of maintaining ANT connections and channel operation. The application can be implemented using an external MCU to communicate with the ANT embedded chip. This could be through UART or SPI. And also the application can be on a SoC, which allows the ANT protocol stack and the radio to be on the same chip. Next, we're going to just describe a couple definitions here as I kind of go into deeper explanations of ANT here. So the first one is a channel, and the channel is what is established between your master endpoint and your slave endpoint, and that's how data is transmitted between two ANT nodes. Next, you have a master endpoint and a slave endpoint. The master endpoint is the primary transmitter, and the slave acts as the primary receiver. Next, over the channel, you have message or packets, and that is data being transmitted over the channel from the master to the slave. Next, we have pairing, and that is the act of two devices, a master and a slave, establishing a relationship between the two so that they can communicate with one another. And finally, searching is the act of a slave endpoint searching for that master channel so that it can begin the pairing process. So let's take a look at the master endpoint. Is the primary transmitter within a channel, and ANT is isochronous, which means that the channel transmits periodically. So as we can see here, the master channel will transmit at a defined channel period. Each of the transmit is going to contain 8 bytes of application-specific data. And the master channel can configure the power output from +4 dBm to -20 dBm. And in addition, in addition to transmitting, the master channel is going to open a receive window. And what that allows for is better coexistence between master channels. And we're going to take a look at that on the next slide here. In addition, the master channel will assign a network key, a channel key, and RF frequency. So this is a look at the coax mechanism. Here we can see a single master channel transmitting at its channel period and a second master channel transmitting at another channel period. As we can see, due to clock drift, we can see that this master channel has now moved into the space of this master channel. This master channel in the receive window detects that transmit and shifts over, so that way you can have multiple master channels coexisting in the same RF space. Next, we're going to talk about how the slave channel searches and connects to the master channel. So in order for a slave channel to connect to the master channel, it needs to be time aware of the master channel. So it's going to need to open up its radio at the same channel period as the slave does. Once the slave finds a master channel, it's going to have to connect to it, and it's then going to synchronize to that master channel. And here we're going to just take a look at how that works. So here we have a master channel transmitting at its channel period. And then the slave is going to start opening up its radio, looking for the master channel. It's periodically scanning. And here we can see in the scan window, we found the master channel. It then synchronizes to that. And every channel period, it's going to open up a receive window and receive that transmission from the slave channel there. So we'll take a look at that just one more time here. So the master channel is transmitting periodically at its channel period. And the slave channel is going to periodically open up a receive window while it's searching. And at this point, we've established a connection here. And at this point, it synchronizes to the master channel. And that's when you open up, the slave opens up the radio just for a short period to receive the transmission from the master. And that's how we achieve such low power communication between the ANT nodes. So let's talk a little bit about pairing. The act of pairing is often difficult on different protocols, but ANT provides some mechanisms to kind of make this a little bit easier. The first thing is by identifying different channel parameters. So the first one is by assigning a network key, a radio frequency, and a channel period. And then going even deeper, each ANT node is going to have a channel ID, and that can be split up between your device type, your transmission type, and device number. And that's essentially your identifier on how the master node will be identified. Some different techniques on how you can connect to a slave to a master is by using wildcard and isolation. So what that does is by wildcarding any channel parameter, that essentially allows you to connect to any one of those values. So how this could work to your advantage is, say you want to connect to a specific device type, you could wildcard your device number if you don't know which device you'd like to connect to, but you can specify your device type. So what that will allow you to do is connect to a very specific device type while not knowing which exact device you'd like to connect to. The next technique is a pairing bit, and a slave will only connect to a master if both the slave and the master indicate that they would like to pair with one another by indicating that they're in a pairing mode using a pairing bit. The next is the inclusion and exclusion list. Here, a slave will only connect to one of the specified master channel IDs listed. And then finally, we have proximity search, and that allows the slave channel to acquire a connection to the master channel based on the proximity using the received signal strength. So now that we've kind of talked about master channels and slave, let's talk a little bit more about the message types. So the first is broadcast data, and that is the default type for the master endpoint. It's going to be transmitting 8 bytes of data per transmit, as we saw earlier. And this is best suited for applications where sensor data is not, where a little bit of sensor loss is acceptable. A good example of this is a heart rate sensor that is transmitting at 4 hertz. Even if just a couple packets are lost, the user really isn't going to notice that dropout. And this offers the lowest power consumption. And let's just take a look at this example here. Here we have the master transmitting to the slave. So here the master is transmitting, and the slave opens up a receive window and is able to receive that transmission. After the master transmitted, then it opens up a receive window itself, and that's for coexistence mechanism. And in addition, we can also send data in the reverse direction. So after the master channel sends the data to the slave then has the option to transmit data back to the master in that receive window there. And after that happens, the master channel will open up a second receive window, again for coax mechanisms. Next is acknowledge data. And again, this transmits 8 bytes per message period. This message type is more suited to control applications where the master channel needs to know that the slave has indeed received that message. So let's take an example, look at an example here. Here we see the master channel transmitting the special acknowledged message. When the slave receives this, it's automatically going to send the response back to the master during that receive window. And then again, the master channel opens up a second receive window for coax mechanism. And this is all handled by the ANT stack. The application only needs to send the acknowledged data, and then the application will receive whether that message was either a success or a failure. You can also send an acknowledged message from the slave back to the master. So here we see that the master is just transmitting a broadcast data here to the slave. Once the slave receives that data, it can then send the acknowledged message to the master in that receive window. And once the master receives that, it's then going to send the response back to the slave, indicating that it has indeed received that message. And then finally, the master opens up another receive window for the coax mechanism. And as I stated before, this is great for control applications. A great example of this is if a byte computer would like to send a control to turn on a light. That's a pretty important command, and that would be best done using a acknowledge message. And if the message was a failure, the application could then decide to send that acknowledge message again until it is able to verify the slave has indeed received that message. Yes? Yes. Yep. That's right. Next, we have data. This is when you want to send data in bulk. You can get data rates anywhere from 20 to 60 kilobits per second, and we'll talk a little bit more about that later. This uses the most power, and how this works is rather than transmitting at the specific channel period, the master channel is going to be sending data as fast as possible. So how that happens is that it sends the packets synchronized to one another rather than at the specific channel period. Each of these, when you send broadcast data, it is also sent like an acknowledged message. So for every data that message that is sent, it is acknowledged and it will be retried up to 5 times. And then if the entire burst message fails, the application will be notified that it was a failure and it can then retry that burst message. And here you see the slave synchronizing with it, receiving data at a very high rate there, with each of the receive windows synchronized onto one another. This is important for use cases when transferring FIT files, and we'll talk a little bit more about that later. Okay, next we're going to talk about the different channel types. So up until now, everything involving the master channel has been described using the bidirectional channels here. And the bidirectional channel is the most common type of connection. And as we saw, it can be used to send just regular broadcast data, acknowledged data, as well as burst data. And this channel is really advantageous is because the radio is only on for such a short period of time, allowing for those ultra low power ANT nodes. And as we saw, the communication is fully bidirectional. So you can simply send messages from the master to the slave. And in addition, when sending data from the master to the slave can respond and send message back to the master. Next, we have continuous scan mode. This has the radio on for the entire time. As a result, it draws much more power. But what this allows you to do is to receive from multiple master channels. And this results in very low latency. And as well, it's fully bidirectional, so you can send messages back to the masters that you've just received from. This is actually quite useful when you want to search for a master device. It can also be very useful for debugging purposes. You can open up a continuous scan and basically monitor all the messages that are happening in the background. Similar to that is the background scan channel. It's also fully bidirectional. But the main difference here is that it's duty cycled. And what that allows is for you to operate channels simultaneously while scanning. In the continuous scan mode, you cannot operate any other channel. The radio is always on. Whereas in background scan channel, you can both be scanning and sending messages at the same time. And you can also use high duty search, which really utilizes the entire resources of the radio. So basically, it tries to utilize as much scanning as possible in between each of the transmits that are happening. And as you can see here, with background scan channel, you can't guarantee to receive every message. Here we can see we receive both messages from the 2 masters, again here. But in this scenario, when the master channel transmitted, the scan channel was not open, and we that one message there. This is quite useful to create asynchronous topologies to monitor messages in the background, as well as to aid in pairing. And it also creates lots of interesting use cases, such as ANT Blaze, which I'll talk about later. So now that we know a little bit more about the slave and master, as well as the different message types and different channel types, let's just take a look at a couple topologies. So one of the simplest topologies is a simple point-to-point network. In this example, we just have a heart rate sensor, and it's sending data to the user's personal display, which in this case is a watch here. In this next example here, we have this network is broadcasting one-to-many. And this works quite well. Here we have again, a heart rate sensor, which is a master channel, and it's transmitting its heart rate value. And it provides a lot of flexibility in that you can have multiple slave channels listening in on that single transmitter. So you can get that data on your bike computer, on your personal display, such as your watch, and maybe any other console that you'd like to. You also have the star network, which is where you have multiple sensors. So in this scenario, we'll have like your heart rate transmitter, maybe power, temperature, and any other sensor that you really would like, any transmitter. And you can have all those transmitters transmitting to a single slave device, which in this scenario is your bike computer. So you can really grab a lot of information from all these master transmitters. And as we saw earlier, because of the coax mechanisms, these master transmitters are going to align themselves such that they're not overlapping one another, allowing this slave device to synchronize to each and every one of those master channels and receive data from all your sensors. Next is the shared channel. In this case, you have one master channel, which is the controllable device, and you have multiple slave channels where they're all peripherals. In this case, you'll have your controllable device sending command, or like controlling all of these peripherals here. This can be useful when a single ANT node needs to receive data from many nodes, or in this scenario, you can have sending a single command to this control device, and that can be sent to each of these devices here. This is slightly different than the one-to-many, is because this master channel can send messages to each individual node without sending it to every single node. And that's done by addressing each individual specific node. In addition, you can also send acknowledged messages to a single device and then receive that acknowledged message back. And finally, you can really mix and match basically to create any network that you like. It's very flexible, and you can basically configure the network to whatever suits your use case. So up until now, we've been talking entirely about the ANT protocol stack, but now let's look at some of the other things that are built on top of ANT. And this includes things such as ANT Plus, which is a managed network, FIT, which is data storage, ANT-FS, which is file sharing, and ANT Blaze, which is a mesh networking solution. So let's first look at ANT and ANT Plus. ANT is the protocol, and being a protocol, it does not define what high-level information may be contained within the data. And ANT Plus is the managed network that defines standards for different ANT use cases to achieve interoperability and assure quality. So a great analogy, a great analogy to this is thinking of ANT as voice and ANT Plus as language. So voice is the physical medium through which we communicate, and ANT Plus is a defined standard for which we can effectively communicate with one another. And what ANT Plus does is it creates interoperability, which allows devices from different manufacturers to talk with one another. And this is advantageous because a user can easily replace one of their sensors or one of their displays without replacing their entire, all of the other sensors that they may have. And within ANT Plus, you have ANT device profiles, and they are open definitions for device interoperability, and they are use case specific, and they are specifically designed for a set of devices that need to communicate with one another. A good example is the heart rate profile, and what that does is it essentially defines where data should be transmitted in that payload that is sent over ANT, as well as how to communicate with one another through the master channel, which is the heart rate sensor, as well as your device, which is the slave. ANT Plus defines the data format, as well as the data exchange mechanisms, how the data is transferred from one another. ANT Plus also defines channel parameters, such as the device type and transmission type, and those are laid out in the ANT Plus device profiles. There are many different device profiles available. Here are just a few of the many that are available, like heart rate, bike lights, bike radar, shifting, suspension. And as you can see, there's a wide variety of manufacturers that all implement each of these device profiles. And what that really allows is every one of these compatible devices to communicate with one another. And that's really great for the end user. They can mix and match whichever sensors they would like. And it's good to note that there's always new profiles in development, and these profiles are always evolving as needed by the use case. Next, I'm going to talk about FIT for data storage. FIT is the flexible and interoperable data transfer protocol, and is a format designed specifically for the storing and sharing of data that originates from sport, fitness, health devices. Is specifically designed to be compact, interoperable, and extensible. FIT is a file format and is extendable and scalable for different device type data. Any FIT compliant device can interpret a FIT file from any other FIT device. So it's platform independent, and it can be used from your device all the way to the cloud. It's designed to be forwards and backwards compatible, so any new additions to the profile will not break compatibility. For more information, you can always look at the FIT SDK that is available on our website. Next is ANTFS for file sharing, and ANTFS is a file transfer protocol. ANTFS defines the transport of large files over ANT between two ANT-enabled devices. And while you can send a FIT file as a regular burst message, it is important to manage the transfer with larger file sizes. And ANTFS defines the state machine for link establishment, authentication, and transport. And a very interesting use case for ANTFS is to do over-the-air software updates. And finally, we have AntBlaze. AntBlaze is a mesh networking solution, and it offers high node count Internet of Things solutions. And just a couple of things that it can be used for is lighting control, asset management, environmental monitoring, and location determination. And this is built on top of Ant. And for those of you who are registered and want to learn more about this, we do have the interfacing a sensor hub with the AntBlaze network, and that is occurring tomorrow at 2 to 4:30 after the coffee break. And that's it. If you'd like to find out more, you can always visit thisisant.com. And thank you.